Hello everyone and welcome to my channel. It's me Bikalpa and we are in the second part of the series implementation of data structures in Python. Actually we had covered part 1 of this video in a separate video where we had discussed the introduction to data structures and some of the very basic data structures in Python. So previously we had discussed big O notation, dynamic arrays, sets, hash tables, stacks, linked lists, doubly linked list, queues and deck. We had actually covered a great session previously. It was quite long, but we have already covered these topics. So in this session we are going to first of all try to do some corrections on the previous video. There were some mistakes and there were something I was missing on those programs. I will correct some of them in this video first of all, and then we will go to the introduction of tree data structures, what trees are, how we can visualize them, and then we will shift our discussion towards binary trees, what they are, how we can use binary tree to implement the binary search tree, and then what a complete binary tree is, and how we can represent complete binary tree using array. Then we will go on to another very important topic that is very frequently asked in examinations as well as technical interviews, the heap data structure, its application, and finally, if possible, if the time permits, we will also discuss about Fenwick trees, which are also called as binary index tree. So first of all, I would like to go to the code of the previous session, and that is very frequently asked in examinations as well as technical interviews, the heap data structure, its application, and finally, if possible, here is the project we worked upon earlier in the last video, and inside the linked list, I think, yeah, I had actually defined a property named num_items, which I had initialized to 0 previously, but we had to increment this num items every time we inserted into the linked list, right? Because here insert front, I have done self.num items equals to self.num items plus 1, but I actually forgot to put that line in insert back. So I will just copy this and paste it here, because whenever you insert into the list, I'm just incrementing the number of items, so that whenever we want to say find the length of a linked list, so we can we can answer that query in constant time. So yeah, in remove front also I will write something like this, but I will do -1, because after removing, certainly the number of items will be 1 less than the previous number of items. And then in the remove back also I will put num items equals to num items -1. Actually we missed that part, I'm sorry about that, but yeah, that's it for linked list. And in the doubly linked list, actually in the constructor self dot num_items equals to, I had put none here, but actually num items is an integer variable. We want to store the number of items here, so I would like to initialize it with 0 in the beginning, not as a none. And then similar to the previous file, we will also write self.num items equals to self.num items plus 1, and insert back self.num items equals to self.num items plus 1, remove front self.num items equals to self.num items -1, and remove back self.num items equals to self.num items -1. So yeah, I think that's it. If you want, you can just add another method that is named as size, that will just return the value of the variable num_items. You can do that yourself, so I will just close this up. So I would like to start today's session, and we will first discuss tree data structures. That is actually our main agenda today. Let me read some of the comments here. Sabu is already here. Hello Sabu. Mission Gimire says, can we make a game using Python? Yeah, I actually already answered that question. Yes, you can make games using Python. Python is a versatile language, but if you mean a kind of 3D games and using those the Unity, Unreal type of engines, I think Python would not be a great choice there. And also, if you go to native application development, native game development, for example, games in Android, games in iOS, then actually Python would not be so great to choose to develop games in those Python in those platforms. There are certainly other frameworks as well as other languages more powerful and more tailored to specifically do those things. So yeah, let's discuss about tree. So a tree is a hierarchical data structure that consists of nodes, and those are connected with some other nodes with a parent-child relationship. What I mean is that there are different type of trees. We will go on to them later, but in general, trees are composed of nodes, and each node are connected to some other node via a parent-child relationship. They are hierarchical, meaning that a parent has child and the child have other children, and so on. So actually we can see a simple tree here. We can see that this node has two children, and this node in turn has 3 children. This node has 1 child. So yeah, this is tree. Actually it quite visually, the tree is visually confusing, because on our intuition, on our real life, trees are in the upright direction, right? But in data structures, trees are just inverted as to what we are used to seeing in our environment. So yeah, it basically is narrower at the top and it is broader at the bottom. So for first of all, discussing about tree, we have to discuss some of the terminologies, and I have collected some of the terminology here. Actually, the first node, the topmost node in the tree, is called as root node, and you have 2 child here. We call them child or children of node A. Actually, D is a child of B, E is also the child of B, F is child of B, and C is parent of G. So yeah, if it occurs, if it is on the upper level, then it is the parent of G. And we can see some of the nodes here. The nodes in the last level, the bottommost level, they are called as leaf nodes. And we can see the height of the tree is 3. That means the number of levels in the tree is 3. So then what are binary trees? Binary tree is a special kind of tree where each node has at most 2 children. So a node cannot have more than 2 children. That is the property that should be satisfied for a tree to be binary tree. Let us see some examples here. B is actually a left child of A and C is right child of A. So that if it has at most 2 children, then we certainly have left and right child, right? So we do not have something as a middle child or something like that, because there are only 2 children at the most. If we see an example here, this is actually not a binary tree. If you may have already guessed why, because this node in particular has 3 children, but a binary tree can have at most only 2 children. So yeah, this is not a binary tree. Now shifting our discussion towards binary search trees, I'm actually building the momentum level by level. So if you understood what binary tree are, now we can define what binary search trees are. Binary search trees are binary trees where for each node the left subtree contains only the values that are less than that in the node, and the right subtree has only values that are greater than that in the node. For example, let us see this tree right here. The 22 is the root node, right? So on the left side of 22, this part, there should be values only less than 22. Yeah, 14 is less than 22, 11 is less than 22, 19 is less than 22. And on the right side of this node, this part, there should be values only greater than 22. 27, 25 and 33 all are greater than 22, right? So yeah, 22 is the root node. The left side of that node should only contain the values less than 22. The right side should contain only the values that are greater than 22. And if we see the node 14 here, the left side of node 14, the node 11, it is less than 14. The right side 19 is greater than 14. If we see 27, the left child 25 is less than 27. The right child 33 is greater than 27. So the left child should be less than the node and the right child should be greater than the node. That is the criteria that the binary search tree should fulfill. Now if we see another example here, this is not a binary search tree, because if we see here, if we see the node 19, the node 19's right subtree, this subtree should have values only greater than 19, right? But if we see here, the value 11, it is less than 19. So if it is less than 19, then it should have occurred on the left subtree of 19, but not in the right subtree of 19. So actually, if 11 is less than 19, it should not be on the right subtree. This is not a binary search tree. Now if we look at a particular node in a binary search tree, we can see that it contains a value, an object known as key, and it has two pointers that are called left and right. They point to another two nodes, right? So its node contains a key, a pointer to the left child named as left, and a pointer to the right child called right. And the entire tree can be represented by root node, because if you get the instance of the root node, you can basically go to every other node in your tree, right? Because you can recursively go to left subtree and right subtree, left subtree, right subtree, and so on. Now if we see the operations in binary search tree, we can see some of the operations on the screen right now. Construct operation constructs the binary search tree with given keys. Insert operation inserts or adds a node with a specified key to the binary search tree. Find operation finds the specified key on the binary search tree. Remove removes the specified key. And then we have some of the traversal, breadth first search, depth first search, pre-order traversal, post-order traversal, and in-order traversal. Basically, this is traversing through the tree in some specified manner. We will discuss them later in more detail. So yeah, these are the operations in the binary search tree. Now we will begin discussing some of the algorithms, some of the operations in binary search tree. The first of all, we will discuss the find operation. This operation is basically done to find if the particular key exists. Let us see some comments here. Dinesh Bala is here. Wow, good going, bro. Thank you. Actually, he is a fellow YouTuber too. I have checked out your videos on YouTube. You are a source of inspiration for me too. Thanks for checking out. So yeah, and the algorithm goes like this. We will first store an instance to the root, and then we will gradually go downwards in the tree. If a particular node has the key equal to the key we are trying to search, then we return that node. Else we will gradually go either to the left subtree or the right subtree. This is recursively going to the left or the right subtree. And if we go on to the left subtree or the right subtree, and then we are recursively going downwards, and finally if we reach the null value, then we will know that the key doesn't exist in the binary search tree, so we will just return null there. That means the key is not in the binary search tree. Let us see an example here. Suppose this is a binary search tree provided to me. Actually, if you can clearly notice here, we have all of the nodes have lesser values in the left subtree and greater values on the right subtree, right? So if we try to find 25, we will start from the root. In all of the algorithms in binary search tree, actually we will have to start from root, because the instance of the root is the only thing provided to us. Whenever we want to reach to a specific node, we will have to reach or we will have to start from the node root node itself. So if we want to find 25, we will begin from the root node, and then we will check if this node contains the required key. Does this node have the required key? No, because it contains 22, but we are required to find 25, right? So we will check whether 22 is less than or greater than 25. If it is less than 25, then we will go to the right subtree. If it is greater than 25, we would have gone to the left subtree. But right now 22 is less than 25, so that means we will not have to check the left subtree now. We have high probability that our required key lies on the right subtree, so we will go to the right subtree. Now we will again check whether this node contains the required key. No, so we will check 27 and 25. 27 is greater than 25, so that we will now go on to left subtree. Okay, in this case we will check again, does this node contain the required key? Yes, because 25 is equal to 25. Now we will just return 25, and then our search was successful. We found the key that we wanted to search. If we clearly see that, we see that on average this algorithm is O of log n, because if the tree is optimal, if the tree is balanced, then every time we are going downwards to the tree, in the tree, we are actually dividing our problem into exactly half, right? Because when we came from 22 to 27, we actually just ignored all the left subtree at once. So that means in every iteration we are just dividing the problem into a half, and then the algorithm complexity is O of log n. But in worst case it is O of n, because if the tree is kind of linear, it is not balanced, then we would have to come from root to all the way to the bottom, and that would be O of n. Now if we see the insertion, it is quite simple too, because we will first start from the root, and then we will go downwards in the tree. If we see the key is already existing in our in our tree, then we will raise an error called duplicate key and then return. Actually you can modify this, and then you can allow for duplicate keys also. You can write that implementation too, but in this implementation I will not allow duplicate keys, and then I will raise error in case a key is a duplicate. And then if the value you are trying to search is greater than the value you found on the node, then you go to the right subtree, else you go to the left subtree, and then you gradually go downwards until you reach to the leaf node, and then finally you insert that key in the place of trap. Okay, let us see example with insertion of 21. So this is the binary search tree given to us, and we want to insert 21 into this binary search tree. So first of all we will see is this node actually equals to 21. If yes, then we would have to return or raise the error that duplicate key is found, right? But no. So if is this greater than or less than 21, we will see that first of all. Actually 22 is greater than 21, so we will have to go to the left subtree now. Now 14 is less than 21. That means we are going to insert on the right subtree, right? Because 21 is greater than 14, and 21 should be inserted on the right side of this 14. So now we will go on to the right side. Now we again compare 19 and 21. 21 is greater than 19, so that we will go on to the right subtree again. But now we don't have any right child, so we will just insert 21 to as its right child, right? So 21 will go as a right child of 19, and our insertion is successful. Now if we see clearly, this algorithm is also O of log n on average, because on the best case, on the average case, if the tree is balanced, then you are just dividing the problem into two halves, and you are just going for O of log n complexity. And then on the worst case, again it is O of n, because if the tree is not balanced and if the tree is kind of linear, then you will have to traverse through all of the nodes to actually reach to the end of the tail of the tree. Now let us see how we can construct binary search tree. So construction is quite simple, because we have already known how to insert a key into a binary tree, right? So to construct a binary tree with provided keys, we will just take out every keys from that list, and then we will just gradually insert into the binary search tree using the previous algorithm, right? So this is quite simple. And again we can clearly see that on the average case, the every insertion will have complexity of log n, and for inserting n keys the overall complexity will be n log n. But in the worst case, the insert operation itself will take n time. So for n keys it will take n time, so that n times n square on the worst case. So on the worst case the complexity is O of n squared. Now here comes the main confusion, the deletion. The deletion is quite complicated in binary search tree. Not that complicated, but I'll cover it. First of all, we will have to find the node to be deleted by searching through the binary search tree. That is our first work. And then there are three cases that we need to pay attention to. So let us consider this binary search tree, and we will go on to the first case. Suppose the node to be deleted does not have a left child. This is the first case. And for that case, what we will do is we will just replace that node with its right child. It doesn't have left child, but it has right child. Then we will just replace that node with its right child. So let us see with an example. Suppose I want to remove 33 here. Let us see 33. 33 has right child, but it does not have left child, right? So the node to be deleted does not have a left child. What we will do? We will just replace this 33 with the right child. That means 40 will go on the place of 33. That means like this, 40 will go on to the place of 33 and 33 will get removed. Let us see another example. Remove 42. If we see the node 42, 42 does not have a left child, right? The node to be deleted does not have a left child. In that case, we just replace that node with its right child. But in this case, the right child is also null. It is empty, So in that case, we can just delete and then it is okay. We can move forward. Now let us come to the second case. The node to be deleted does not have a right child. In the previous case, the node to be deleted did not have the left child, but now the case is that the node to be deleted does not have right child. In that case, the solution is to replace that node with its left child. Let us see an example. Suppose we want to remove 14 from this array, from this tree. So 14 has left child, but it does not have right child, right? The node to be deleted does not have a right child. So in that case, what will we do? We will just replace that node with its left child. That means 11 will replace 14 and 14 will just be deleted. Let's see. Yes, like this. Now the removal is successful. Now we come to the third case, that is the most complicated case. In this case, the node to be deleted has both left as well as right child. Now in that case, we need to actually swap that node with the smallest node on the right subtree and recursively delete that node down as it moves down the subtree. Actually, I will show you with an example. Suppose I want to remove 22, that means the root node, right? So first of all, to remove the root node, I cannot remove it directly because that will create a loophole here, So first of all, what I'll do is I will first of all find the smallest element, the smallest node on the right subtree of this root node. The right subtree is this part, and the smallest smallest node on the right subtree is 25, because 25, 27, 40 and 35, among them 25 is the smallest node, right? So we will just swap 25 and 22. Now 25 will become the root node, 22 will come down. Now we will again try to delete 22, but in this case this will reduce down to the first case. If you remember, this does not have left child, right? So we can safely delete this and then we are done. We can clearly see the algorithm is O of log n. You can clearly see that because for the deletion, actually you go to one of the subtrees and then find the minimal value. You just replace that and then recursively go on to delete that, right? So it is O of log n because you have just ignored the total left subtree for consideration, right? Now let us go to some of the traversal in the binary search tree. Traversal means to start from the node and visit each and every node in the binary search tree. So first of all comes the pre-order traversal. What pre-order means is that first of all we will visit a node, and then only we will visit the left subtree, and then we will visit the right subtree. Actually our visit order is pre-order. That means first of all visit the node and then only go to left and right subtrees, right? That means pre-visit, that is pre-order traversal. Let us see with an example. We will start from 22. So first of all visit 22 and then only go to the left subtree. So visited nodes, 22 is already visited. Now go to left subtree. Now visit 11, because we have to first visit the node and only then we go to the child, the left subtree. Now 11 is visited. We go to 10 and visit 10. Now it doesn't have left child, it doesn't have right child, so the recursion will eventually come back, Then only we go to the right child. 19. We come back. We have already traversed the left subtree, right? Then only we go to right subtree. We go to 27 and we visit 27 first, because we have the order like this. First visit the node and then only go to the left subtree and then only go to the right subtree, right? So first of all visit 27 and go to the left child of 27, and then visit 25 again and then go to the left child, but it doesn't have left child. If it doesn't have left child, then go to the right child. It also doesn't have right child, then go back to parent, and then now the left subtree is already traversed. Now go to the right subtree. Now again first of all visit 40 and then only go to the left subtree, and then visit 35 again. Now it doesn't have left child, it doesn't have right child, return back to parent. Now it doesn't have right child, return back, and then we have already traversed all of our nodes. This is the pre-ordered traversal of our binary search tree. We can clearly see that this is O of n, because we are basically going from root to every other nodes, right? So if we are visiting all of the nodes, then actually this is clearly O of n. Now let us see in order traversal. So the difference between pre-order and in order is that the pre-order first of all visited the node and then the left subtree and then the right subtree, right? But in this case actually you first of all visit the left subtree, you gradually recursively go to the left subtree to the tail of the tree, and then you visit the node and then only you visit the right subtree. This order matters. This order actually defines what in order traversal is. So first of all left subtree and then only that node and then the right subtree of that node. Let us see the example here. We start from the root, but we do not visit it directly, because first of all we go to the left subtree and then only we visit the node and then we go to the right subtree, right? So we go to the left subtree 11, but then again we do not visit 11, because we will first go to the left subtree and then only visit that node and then we come to the right subtree. So we go to 10, but then it doesn't have any child, it doesn't have any children, so we can safely visit this and then we come back. Now we can visit 11 because we have already visited the left subtree. Now it is the turn of the node itself, and then now is the turn of its right child. We visit 19 and then we go back and then we go back and visit 22, because all of the nodes in the left subtree are already visited. Now it is the turn of the node itself. Now it is the turn of the right subtree. We go to the right subtree, but we do not visit 27(8) because we will first have to go to the left subtree and then only we come back to the node itself. So go to the left subtree 25. We visit 25 because it is the leaf node. It doesn't have any left child or right child. And then go back to parent, visit the parent, because we have already traversed all of the nodes in the left subtree. And then we go to the right subtree, but we do not visit 48. First of all we have to visit the left subtree. We go to 35, visit it because it is the leaf node, and then we come back. We visit 40 because we have already traversed the left subtree. It is the turn of the node itself, and then we go to the right subtree, but it doesn't have right subtree, so we just return back to the root. And this traversal order, it is known as in order traversal. And this algorithm is of O of n complexity, and if you notice something special here, actually the keys are in sorted order. You can see that 10, 11, 19, 22, 25, 27, 35, 40. The keys are in sorted order. This is the unique feature of in order traversal. The keys are always in the sorted order. Now talking about post order traversal, the only thing different here is that first of all we go to the left subtree and then to the right subtree, and then only finally we visit the node, right? Actually this visit node was in between of the left subtree and right subtree traversals in the in order traversal, but in this case we can clearly see that visiting the node itself will occur only after all of its left subtree and all of its right subtree are visited. So let us see an example here. If you guys do not have subscribed to my channel, and I request you, now is the time. I actually plan to reach 400 in this stream, so yeah guys, make it happen. I'm currently at 350 around right now. Let's hope I reach 400 today. So yeah, we start from the root, but we do not visit 22.8 because to visit the node itself we have to visit all the left subtree nodes and all the right subtree nodes, and then only we come back to the parent. So first of all go to left subtree. We still don't visit 11, we again go to left subtree. Now we don't have any other child of 10, so we can visit it, and then we return back. But now still we do not visit 11 because it has we have already covered all the nodes in the left subtree, but we haven't covered all the nodes in the right subtree, right? So first of all go to left subtree, then go to right subtree, and then only visit the node finally. That means that is what post order means. So first of all go to right subtree, visit 19, and then come back. Now only visit 11. We can visit 11 now, and then we go back. We still cannot visit 22 because we have not visited all of the nodes in the right subtree, right? So we first go to right subtree. We still cannot visit 27 because we have to first go to the left subtree, and now visit 25 because it is the left node. Go back, but we cannot still visit 27 because we still have some nodes left in the right subtree. So go to right, do not visit 38, go to left, visit 35 because it is a left node. 35 is visited. We go back, now we visit 40. If we had some other children here, on a right child of 40 here, we would have to first of all visit that child and then only 40, but since 40 do not have any right child, we can actually visit it on the way. So we visited 40 and then we go back. Only now we can visit 27 because left subtree as well as right subtree has already been visited. So we go back again and we visit 22, and finally we can see that 22 is also visited because left subtree as well as right subtree is already visited, and 22 is the final value. So yeah, we have already traversed this tree in post order. This clearly is O of n because if there are 100 nodes in the tree, we have to traverse 100 times, right? So the number of nodes to be visited is n, so that this algorithm is O of n. Sabu asks a question: what is the difference between binary and binary search tree? Yeah, this is very good question. Actually, binary search tree has a unique property that all of the children in the left should have value less than, and all of the children in the right should have value greater than. For example, in this 22 has its left subtree here, 11, 10 and 19. All of these values are less than 22, and 27, 25, 35 and 40, all of these values are greater than 22. So that is a unique property of binary search tree that should be satisfied. But in binary search tree, this condition is not necessary. You know, if there was 22 here and 11 here, then we could have said that this is a binary tree but not a binary search tree. But you know, if we have 11 here and 22 here, right now in this condition, this is a binary search tree as well as a binary tree. You know, all the binary search tree are binary trees themselves, but they have another unique property, that all of the nodes should have the values less than themselves in the left subtree and and greater than themselves in the right subtree. That is extra feature that a binary search tree should have. That is not necessary in the binary tree. I hope your question got answered and you understood. Let's move on to the next algorithm, that is the depth first traversal. So yeah, if you remember the last video, we talked about stack data structure, and in the application of stack data structure, I had told you that they are explicitly used in the depth first traversal of trees. So yeah, here we are. We use stack to do depth first traversal. Actually, depth first traversal means that we will go deep down to the tree first of all, you know, dive deep, and then only come back, you know, and then return back. So first of all, we will create a stack and we will push the root into it, and then while the stack is not empty, we will just pop a node from the stack and then visit that node, and then we will just add all its you know, its left child as well as right child into the stack, and then we repeat again. We pop the stack again, we visit the node, and then we put the left and right child of that node into the stack again, and we will repeat that step until and unless the stack is empty. So let us see with an example. In this tree, first of all, we will visit from the 22. First of all, we will have to you know, push the root node into the stack, right? So I first push the node 22 into the stack, so stack will contain 22 here, and now I pop the stack 22. We will visit 22, so it comes under the visited nodes. I mark 22 as visited, and now I will insert its left child as well as right child into the stack. That means I will insert 27 and 11 into the stack. Now I will pop another value from the stack. That means in this case 11 gets popped out. I will visit that node. That means it comes under the visited node, and then I will insert its left child as well as right child into the stack again. That means 19 and 10 are inserted into the stack. So now we pop our stack again. In that case, we take out 10. We will visit 10. So it is marked as green color. And now we will push its left child as well as right child into the stack. But in this case, this node does not have any left child. This node does not have right child. So we will not need to push anything. So we will just pop another value now. 19 gets popped out, and we will visit 19. 19 gets marked with green color, and we will push the child, you know, the children, left child as well as right child into the stack, but this does not have any, you know, left child as well as right child, so we will not have to push anything here. So now we will pop the stack again, 27, and we will basically insert both of its child into the stack again. And 27 is already visited, and we inserted, you know, we pushed 25 as well as 40 into the stack, and then pop out 25, visit it, and then insert its children into the stack. Right now it doesn't have any children, so we need not push anything. Now again pop 40 and visit it and insert its children into the stack again. In this case 35 needs to be inserted into the stack, and now pop 35, visit it, and finally we will have our stack as empty because 35 doesn't have any child, and we will not have to push anything into the stack. And the next time we want to pop something out, we can clearly say that there is nothing in the stack, so that our stack is empty, and we have basically completed the depth first traversal. This is the order of depth first traversal. If you can see that, you can clearly see that first of all we go to 22, right? So first of all we visit 22 and 11 and 10. That means we are basically going deep down inside. First of all, you know, we are not visiting 27 or we are not visiting 25 or 40. We are going deep. That means depth first, you know, we go to deep first, and then only we come back to visit other shallower nodes. And this algorithm clearly is O of n. Basically all of the traversal in the trees are O of n, because we need to traverse we need to visit every node, and that is clearly O of n. Now go to the breadth first traversal. This is basically quite different, because in the breadth first traversal we will try to traverse not too deep down, but first of all we will try to traverse all of the nodes of the first level, and then all of the nodes of the second level, then all the nodes of the third level, and so on. And for that we will use queue data structure. If you remember, we had already covered a queue in the first video, and we will use it here. First of all, we enqueue the root, and then while the queue is not empty, we just dequeue a node, visit that node, and then we enqueue both of its left as well as right side. Basically the difference between the depth first and breadth first in terms of implementation is that depth first uses stack and breadth first uses queue. Rest of the algorithm is similar. So let us see with an example. First of all, we enqueue the root, right? So in the queue we insert 22 into the queue, and now we dequeue the queue. We get 22, right? We visit 22 and put it under the visited nodes, and then after that we will have to enqueue both of its child. That means we enqueued 11 as well as 27. They are inserted back into the queue, and now we remove an item from the queue, and in the queue we will basically first of all remove 11 and then 27, because queue follows first in first out principle, not last in last out principle. Stack was last in first out, but queues are first in first out. So we will first of all take out 11, visit it, mark it as visited, and then we will insert both of its child into the stack again. That means 10 and 19 are sorry, not into the stack, into the queue. So 10 and 19 are inserted into the queue again. Sabu asks a question: depth first search. In depth first search, how many times you have to visit a node? Basically in depth first search you have to visit every node, each and every node only once. That means you have O of n complexity. Actually due to the recursion, you will see that while returning from the recursion you may visualize it as some nodes being visited twice, but that is not the case. Actually we visit each and every node only once, and we either print that value or mark it as visited, or do some operations with that, but that is clearly O of n. So that if you have 1 million nodes, then you will have to visit 1 million nodes. If you have 1 trillion nodes, then you have to visit 1 trillion nodes. That is quite fairly straightforward. So we visited 11 and inserted 10 and 19 into the queue. We dequeue 27, visit it, and we insert both of its child into the queue again. That means 25 and 40 will get inserted into the queue, and we take out 10 because that is in the first of the queue. We visit it, 10 is visited, and then we insert left as well as right child of 10 into the queue, but right now 10 doesn't have any child, so yeah, we will not have to insert anything here. And then we go to dequeue 19, visit it, it doesn't have any child, so nothing needs to be inserted into the queue. Now again take out 25, visit it, there is nothing inside as a child of this 25, so we will not need anything to insert here. And then take out 40 and visit it. 40 has one child, so we will have to insert 35 into the queue again, and then take out 35, visit it, and it doesn't have any child, no left child, no right child, we will not have to insert anything here. And then finally when we want to dequeue something, we will discover that the queue is empty, right? So if the queue is empty, we will know that the breadth first traversal is complete, and we will just stop here. Basically this algorithm is also of n. I will not have to explain that because you have to visit each and every node once. So let us see some limitation on binary search tree. The limitation is quite straightforward here. What you can see is a binary search tree here. This is a binary search tree, and if you can see, all of these nodes in the right subtree of 22 are greater than 22, right? And it all of them follow the property of binary search tree. But if our binary search tree grows like this, skewed in one of the directions, either in the left side or the right side, then it poses problem for us, because suppose if you want to find 55, you have to go through each of these nodes, right, like this. And if you have 1 million nodes stacked up like this, then you have to go 1 million times to find that node, right? So basically in that case it can take up to O of n time, and that is quite bad. We do not want that. So the solution is using the self-balancing trees, for example AVL trees, and if possible we will cover it on the next session. I haven't thought of covering it in this session, but basically what self-balancing trees are is that whenever we insert a node, the tree detects if the tree is skewed in one direction, and then the tree automatically balances itself to be balanced, to have more or less the same number of elements in the left subtree as well as right subtree. And finally, talking about the applications of binary search tree, they are actually used for efficiently storing the sorted data for quick searching, and it is used in Unix kernel for managing a set of virtual memory areas. A binary search tree by itself has the term search in it, so yeah, we can clearly see that it is used in search indexing problems, because we can search for a key in O of log n time, which is quite good. Now is the turn where we will actually implement binary search tree in our code. And then for that I actually will go to data structures folder, and I will create a new module called binary search tree.py. If you guys have any problem understanding the code itself, then you can ask me in the chat box. So first of all, I will write the declaration for the particular node, right? So I will define class node as it will basically first of all contain a key, a left pointer as well as a right pointer, right? So what I'll do is I will first define a constructor, and I will define some of the properties here. Self.key equals to key. I will basically pass the key from here to the constructor itself. Self.left equals to left, and self.right equals to, sorry, it should be none, because when we first create a particular node, then we will want to have the left initialized to none and right initialized to none. So this is the definition, a blueprint for a particular node of our binary search tree. So moving forward, we will write the class for binary search tree. Class binary search tree, and we will first of all define the constructor. So our binary search tree will basically contain a root node, which will be null in the beginning. When we first create the binary search tree, right, it will be null in the beginning, and we will later update it. And self.num nodes, I will create this variable to actually store the number of nodes in the tree itself. So actually I would want to create a binary search tree with provided keys, right? And for that, what I'll do is for key in keys, I will basically do self.add and then add that key into the binary search tree. We haven't written this add method yet. We will write it later on. So if we first want to insert into the binary search tree, we will have to write a recursive algorithm. Recursive means we are calling the same function again and again. So what I'll try to write is I will try to write a function named add_recursive, and which will take the self as a mandatory first parameter, and it will take node as a second parameter, and an item as the third parameter. What I'll want to do is actually I want to define this method as a recursive method, by implementing recursion. And what this method does is it inserts an item into some subtree of node, right? So node is a parent tree, a parent node. You know, it can be a root or it can be you know, any parent node, and we will basically use this node to basically go down into our tree to find the appropriate position for this item, and finally insert that item in the tree itself. So in every recursive method we will have to, you know, define a base case so that the recursion will end. And in this case the base case will be something like if node is none. That means if we have already reached to the root of sorry, to the leaf node, you know, and if we do something like the node dot left in the leaf node, then we will not have anything as a left or right child of a leaf node, right? So on the leaf node the left child as well as right child will be known, and in that case this particular condition is satisfied and our recursion will end there. So in that case what I'll try to do is I'll try to create a new node with an item. This item gets passed into the constructor as a key, and then our node class will get instantiated and a new object will be created, and that object will have its left as well as right as none, and then that will be assigned to node variable. And if that is not the case, for example, if, you know, item is less than node dot key, that means the item we are trying to insert is less than the item particularly in a particular node, then we will have to, you know, insert that item in the left subtree, right? Because if the item to be inserted is less than the item in the node, then we will have to go to the left subtree. If the item is greater than the item to be inserted, if the item to be inserted is greater than the item in the particular node, then we will have to go to the right subtree of that node. So in this case what we will do is we will do node dot left equals to self dot add recursive. We are basically calling the same function here, and node dot left item. That means in that case we will call the add recursive function again, and as a node we will pass node dot left, that means the left subtree, and then say the same item. What it means is that someone is trying to say me say to me that, you know, insert this item. Suppose I am a node, right? So I am node and someone is trying to tell me that insert this item. So basically first of all I check that the item is less than what I currently have, right? So what I will do is that I will say to my left child that insert this item, and I will handle that task to my left child. So basically this is what we are trying to do. We are trying to insert item into the left subtree. If that is not the case, then what we will do is node dot right equals to self dot add recursive node dot right and item. In this case we are trying to say that we are trying to say to the right child that insert this item. It is now to be inserted in the right subtree, because this condition was not satisfied. This means item is greater than node dot key. In that case the correct position for the item would be on the right subtree. You know, basically we have to do this because in the binary search tree all of the items in the left subtree of a particular node should be less than that node, and all of the items in the right subtree should be greater than that node. So to enforce that property we would have to write these cases. Still reading the comments. Yeah, nothing new here. So yeah, let's go back. And you might be confused that why am I doing node dot left equals to something like that. Basically in this Python programming language this node is passed as, you know, as a separate instance of the node itself. So whenever we do something like node equals to node item, actually the original node will not get will not get updated. So for that we will have to create a new node, and we will create a new left subtree, we will create a new right subtree, and then basically that left subtree will also have a new left subtree, and then we will try to recursively construct a new tree, and then finally we will return that tree from while we return from the recursion, right? This is the way we will write the recursive algorithm of adding a particular item to a tree, binary search tree. What this 20th line does is, first of all, it will call self.addRecursive on node.left, and by some means the item will get inserted into some place at left subtree, and then this will give me a new left subtree, right? Left subtree but updated left subtree, and then I will just assign it as node.left. That means the node.left will will ignore its old value, and it will now start to store a new value. The new value is that the new left subtree that contains item. The old value of left subtree did not contain item, but new value of left subtree will contain the item, and that is basically what is getting assigned to node.left. And the same is the case for node.right. In node.right, we have actually inserted item into the right subtree, and then we return that right subtree as a whole, and then we assign it to node.right. That means node.right will now contain the new subtree, not the old subtree. We are basically overwriting here, and then we finally return node, and finally after this recursion ends, basically it will return the same node as we had passed originally in this argument, but now the tree will contain item. Previously this node did not contain item, but now this node has item down somewhere. We do not know where, but it has item already inserted down somewhere along its left or right subtree. So basically this is the recursive algorithm, and I still have to define this add method. So what I'll do is I will define add self item. In this case, what I'll do is I will say self.root equals to self.addRecursive, and what I'll do is I will add into the self.root, I will insert item. What this means is I will just recursively add item into the root, into the root node. That means somewhere down in the tree, and then this will basically give me an updated tree that contains item, and we will assign self.root to point to now the updated tree, not the old tree but the new tree that contains item. This is basically what we are trying to do here. And finally, self.numNodes equals to self.numNodes plus 1. So yeah, we have already written add recursive. So basically let's go on to write some other methods. If you guys have any queries, you can go on to the chat and ask me. And if you guys do not have subscribed to my channel yet, I request you do so, because I have the target of reaching 400 today. So I just wish I reach 400 today. And now going to another method. I don't know what I should write first, breadth first search or pre-order traversal or post-order traversal. So let us first of all write depth first search, right? Okay, first of all define depth first. Let's say depth first list. We will basically create a new list and return. Okay, and then I will create a visited list that is empty. At the first, I will create a new stack, and for creating a stack, I will basically have to import stack from this module. We have already written that. So what I'll do here is first go to the beginning and say from data structures dot stack import stack. I will need queue also, from data structures dot queue import queue. So we will need these two modules, these two classes. I will come back here. I will create a new stack as such, like this. I have just created a new object of a stack class, and then first of all I will do stack.push self.root. That means I have pushed the root into the stack at first. Now what I'll need to do is, while not stack dot is empty, until and unless the stack is empty, I will just pop a value from the stack, and then I will basically add it to visited list. Node dot let's say key, node dot key, right? Because we have key defined here, node dot key. So first of all, pop out a value from the stack and then visit that node. And what I'll do is, if node dot left is not none, I will say stack dot push node dot left. If the left child is not none, is not null, then we will push the left child into the stack. Also, if node dot right is not none, in that case stack dot push node dot right. And then finally, after this while condition is, we come out of this while condition, in that case the stack is empty, then we will just return a visited list so that we can access it from outside. So yeah, this is depth first search, depth first list, traversal, let's say. And this is clearly O of n because we have to traverse all of the nodes. It is similar to define breadth first search. In this case, all of the other things will be similar. Visited list equals to empty list, but we will create a queue instead of a stack. We had created a stack here, but now we will create queue, and then we will queue dot in queue. We will insert self dot root into the queue, and while not queue dot is empty, until and unless the queue is empty, we will basically do node equals to queue dot dequeue. Instead of stack dot pop, we will do queue dot dequeue, and we will just say visited list dot append node dot key. We are basically visiting that node, and if node dot left is not none, we will just do queue dot in queue node dot left, and if node dot right is not none, queue dot in queue node dot right. And finally, after this while loop is complete, that means all of the nodes are visited and all of the nodes are inserted into the visited list, we will just return visited list. So this is depth first search. The only thing difference between them is the use of stack versus the use of queue. So yeah, let's read the comments. Still no comments here. Okay, then I think you are understanding quite a lot. No confusion. That is really very good. Let's go to the next method, and I think we will do in order traversal. So for in order traversal, we will define a recursive function. I will say in order recursive, and self is the mandatory first parameter, node will be the second parameter, and li will be the third parameter. Let's say it as visited underscore list. Since this is the recursive function, I am actually passing the visited list into the function call itself. Actually, we had not implemented this algorithm, the breadth first search, as a recursive algorithm, so we did not need to pass visited list as a parameter itself, but in this case we have passed as a parameter. So basically we are just trying to recursively go down into the tree, and we are trying to populate this visited underscore list with the nodes in order fashion. So we basically, the in order means that we will first go to the left subtree, and then we will visit the node, and then we will go to the right subtree, right? So for the recursion and basically for every recursive functions, we will need a base condition so that our recursion will end. And in this case, the some base condition will be something like, you know, if node is not none, or sorry, if the node is none, if node is none, we'll just return visited list. This means the recursion will end here. This is the base condition. Now basically if you remember, in order traversal, we will first of all visit the left subtree, and then visit the node itself, and visit the right subtree, right? So for visiting the left subtree, what I'll do is I will do self dot in order recursive, and then I am recursively calling the same function, but now in place of node I will pass node dot left. I am passing the left subtree, and in case of visited underscore list, I will also pass visited underscore list. The same list I will pass into another call, and visit the node itself. For visiting the node itself, what I'll do is I will say visited list dot append node dot key. That means this particular node is visited. Visited list will contain this node. That means the node is visited. We have created visited list actually for that purpose, that very purpose. So this means the node is visited. And finally visit the right subtree. For that we will do self dot in order recursive node dot right and visited list, and then finally we will return the visited list. This is in order traversal in recursive fashion. So if you understand this, then you can clearly do pre-order as well as post-order traversal. For example, if I say pre-order traversal self node visited list, the same base condition exists here. If node is none, then return the visited list. Now only the order is different, right? So in this case we will first visit in order recursive, we visited the left subtree, we visited the node itself, and then we visited the right subtree. But in this case we will first of all visit the node itself. That means visited list dot append node dot key, and then we will visit the left subtree, self dot in order recursive, not in order, it's pre-order. I will actually define it as pre-order recursive, so that we will actually in fact know that this algorithm is a recursive algorithm. So pre-order recursive, and then inside it we will pass node dot left and visited list. This means visit the left subtree and finally visit the right subtree, node dot right and visited list. Visit the node itself, visit the left subtree, visit the right subtree, and finally return visited list. So coming to post order, I will basically write this quite quickly. Return visited list, and then first of all we will go to the left subtree and then to the right subtree, and then only we will visit the current node. So in that case node dot left, visited list, self dot post order recursive, node dot right and visited list, and finally we will do something like visited list dot append, and we will append node dot key, and we return visited list. This is the post order traversal, post order recursive. So yeah, these are the recursive algorithms, but we will also write some of the we will write a simple method for these three methods too, because when the user tries to get in order traversal list or pre-order traversal list, he does not want to pass this node parameter by himself, right? So what I'll do is actually here, after in order recursive, I will say in order list, and then this will basically return I will just call the in order recursive function return self dot in order recursive, and as a node I will pass self dot root, and as a visited list I will pass an empty list. I'm just starting the recursion from here, and then basically this recursion will take place. Finally it will return a list, and then that list is returned again by this function, so that in order list will return a list as a whole. And I will also write pre-order list. This will basically return self dot pre-order recursive, self dot root, and empty list, and finally post order list. Actually I forgot def keyword here. Def post order list return self dot post order recursive, self dot root, and visited list equals to empty array. Actually I passed empty array here, yeah, so I will pass empty array here too. So we have already covered all of the traversal algorithms, and the only thing remaining now I think is the finding a particular key, right? So let us write the algorithm for finding a key. So first of all I will say find particular key. The self is a mandatory parameter and key is the second parameter. So I will just basically write find key, and basically how this algorithm will work is first of all I will create a variable called node, and it will point to self dot root. I will start from the root, and until and unless I have reached none, that means node is not none, right? While node is not none, I will check if that node contains the key I am searching for. This is the key I am searching for. If this node contains the same key, then I will return that particular node. But if not, then I will check if the key inside that node is less than the key I am trying to search. In that case, I will basically update the node to be node.write, because I have to start checking to the right subtree now. And if that also doesn't happen, I will say node equals to node.left, and finally return none. Basically this return none will get executed only if the key is not found, because if the key is found here, basically this function will already return from inside here, and if the function execution reaches here, that means that the key is not found, and in that case we will return none. So writing another method, we will have to write remove function, and remove is the quite one of the most complex algorithms, as we have already discussed. So we will write it by breaking down into three cases. So first of all, let's write a remove recursive algorithm. So define remove recursive self node item, this node is particularly our ancestor node, and this item is the item to be removed. If you have understood, you know, the add recursive function, basically you will have no trouble understanding the remove recursive function, because we will actually you know, implement the same idea here. First of all, we will provide the base condition for the recursion to end, and that is if, you know, node is none, that means we have already reached to the bottommost level, we will just return none. And if item that is to be removed is less than node dot data or node dot key, that means we will say we update the node dot left to be a new subtree which is received after removing the item from the left subtree, right? We actually use the same syntax here. Add recursive, yeah, node dot left equals to self dot add recursive node dot left item. That means insert the item to the left subtree, and this will give me a new left subtree, and we will assign that back to the existing left subtree, so that the existing left subtree will point to the new subtree. We are basically doing the same thing here. That means we are trying to remove the item from the left subtree, and this will give me a new subtree, and I am assigning that to node dot left, so that the node dot left will now point to a subtree that will no longer have item. The item is already deleted. If this is not the case, if item is greater than node dot key, then node dot right will be equals to self dot remove recursive node dot right and item. That means remove the item from the right subtree. This will create a new right subtree and assign it back to the right subtree. And finally, if this is not the case, if the item is not less than and not greater than, that means what is the remaining condition? If the item is equals to node dot key, and in that case we are trying to remove that item, right? So if this case is not satisfied, and if this case is not satisfied, then we basically come to this case, and this case means that the item has been finally found. Because if it is not less than, if it is not greater than, then what it is equals to, right? But then again we have to go to three cases, you know. Case 1, that means there is no left child. So how will we say that in code? Something a node doesn't contain left child. For that I will say if node dot left is none. That means node dot left is none means node doesn't have left child. In that case, what I'll try to do is I will just try to, you know, replace that node with the right child, right? So for that I will store right child into a new variable, and then I will say node dot key equals to none. I am just trying to, you know, remove this node, so that I am just assigning its key as none. And then I will also say node equals to none. I am basically assigning this particular node to be none because I am trying to delete it, right? And then I return right child. So what this actually is doing is that, you know, if I return a right child after deleting a particular node, then when we do node dot right equals to, and then we assign this function right here, if this function returns right child, that means that right child will itself get assigned to node dot right. You know, there is a very confusing topic right here. Suppose for example you called this function and then it reached to this case, it basically, you know, returned the right child of that particular node, and then you assign the right child as the right child of the child, right? Basically this is what we are trying to do. And in that case, you know, you have successfully deleted this node, and you have updated node dot right to be a right child. So yeah, we go back and then we go to case 2. What is the case 2? Case 2 is if there is no right child, that means node dot right is none. In that case, replace that node with left child. That means we will basically store left child in a new variable, and then we are storing it in a new variable because we are later doing node dot key equals to none and node equals to none, right? So if we do these two operations, then the value inside the node itself is get lost. So before deleting it, we are trying to store the left child inside it, and then only we will delete it, and finally we will return left child. So yeah, so far so good. And we'll go to the case 3, else. And in this case, as we have already discussed earlier, we will need to find the maximum element in the left subtree or find the minimum element in the right subtree. You can do both of these. You can do either of these, either you find the maximum element in the left subtree or you find the minimum element on the right subtree. So I think I will do something like finding the maximum element in the left subtree. For now I will just say pass. I will come back to it later. First of all, I will write that another function to find the maximum element in the left subtree. So let us write finding the maximum element in the left subtree. For that, I am writing a new method, find max in left subtree, and then I will first of all go to the left subtree, and then I will go until and unless I reach to the leaf node, right? I have to reach to the leaf node because the minimum element will always be in the leaf node, while not node dot is leaf. Basically I haven't written node dot is leaf, right? I will write it later. For now, consider that this function already exists. So in this case, I will just say node equals to node dot right. That means I am trying to go as far right as possible because I have to find maximum, right? To find maximum, I have to go right, as far right as possible, because in a binary search tree, the greater value will be on the right side, the smaller value will be on the left side. So this is why I am trying to go as far right as possible in the left subtree. This is what we are trying to find, finding the max in the left subtree. So finally, if the node is leaf, then we return node. So yeah, first of all, let us write this isLeaf method in the node class. A particular node is leaf node if and only if it doesn't have left child, it doesn't have right child. That means its left child as well as right child is none. In that case, that node is a leaf node. So what I'll say is return self dot left is none and self dot right is none. If both of these cases are satisfied, that means there is an AND clause here. So self dot left is none and self dot right is none, then this will return true. So coming back to our function here, so this will basically give us the maximum in the left subtree. So let us go back to the function we were writing here, and basically we have we have to call this function from here. So self dot find max in left subtree of which node? Of node that is stored in the node variable itself. We get that node from the formal parameter. So yeah, we find the maximum value in the left subtree, we store it in a temporary variable, and then do node dot data equals to temp dot data. Actually we are trying to swap the value, right? Because we find the minimum element in the we find the maximum element in the left subtree and then swap the value. right? So we say node.data equals to temp.data and node.left equals to, now we will try to remove recursively after swapping, we will try to remove node.left. So self dot remove recursive from node.left, from the left subtree we will try to remove temp.data, because after swapping temp.data will contain node.data. Actually node is the thing we are trying to delete, so to delete it we have to recursively again call it, wherever that value goes down to the tree after swapping, we will go to that part and then remove it from there also. And suppose it reaches to 100th node and we go to the 100th node and then again try to remove it. If it reaches to the 1000th node and then we go to 1000th node and then again try to remove it, until and unless it reaches to the leaf node, or or this case 1 or case 2 is satisfied. In that case they will just be deleted and the right child or the left child will be returned. So until and unless case 3 reduces to case 1 or case 2, we will recursively go down until and unless these two cases are satisfied. And finally, after updating the node itself, we will return node, because we passed the old node here. We say remove item from the tree starting from this node, and we have done something here, and this will remove the item from that tree. And finally we return the new tree that has the item removed, and we will use this tree to override the existing tree. So yeah, I will write remove self item as a simpler method. What this will do is, this will self dot remove recursive, and then it will remove from self dot root the item. But first of all we will have to check if the item exists or not, right? So first of all, to do check if the item exists, because before removing an item we have to check whether the item exists or not. So let us go to read some of the comments here. Pratigya is here. Good going, sir. Hello, Pratigya. Let's go back to our code, and then we are trying to write. We have already written the find, right? So yeah, we can use it. Yeah, we can use it. We will say node equals to find, or let's say something like this, something like if self dot find, we try to find the item, and if this is none, then we will just say erase our runtime error, the key you are trying to remove does not exist in the tree. Else what we'll do is we will remove the item. So far so good. Basically this is just checking whether the item we're trying to remove is existing on the tree or not. If it doesn't exist, then we will raise a error saying that the item doesn't exist. And after removal, self.numNodes equals to self.numNodes -1. So yeah, this is it. I think we have already covered all of the basic methods in a binary search tree. Let us write example code and then test it out. Let's say bst.py. Oh, it's py. Okay, from data structures dot binary search tree input binary search tree. we will create bst equals to binary search tree. We create a new tree, and then let's do bst dot add. We try to add 23. bst dot add, we try to add 11. bst dot add, let's add something like 10. bst dot add 13. Now I will try to print bst dot let's say breadth first search. Where is breadth first search? Actually I want to make it breadth first list. This name doesn't make quite sense there, so I'll make it breadth first list and call breadth first list from here, because it returns the list in a breadth first manner. So I'll go here to my terminal and I will just run it from here, and then it gives me 23, 11, 10 and 13. I don't know if it's correct or not. Let's see. (23, 11, 10 and 13). I think that is not quite correct, is it? Let us try depth first. Oh, sorry. Actually this requires a positional argument, keys, and basically here what I can do is I can say the keys has default value of empty list. So if I do not pass any key, any set of initial keys, then this will take empty list as the default parameter. So this will be working. Now again running 23, 11, 13 and 10. I think that's good. Breadth first list 23, 11, 10, 13. I need to visualize this first. Basically 23 inserted to the root, and then (11) comes, we insert it here, and 10 comes. For 10 we will go here, and 13 comes, 13 will go here, right? So for going breadth first, we will go 23, 11, 10, 13. 23, 11, 10, 13. Yeah, that is correct. And for depth, for breadth first search, depth first search, sorry, this needs to be commented. Quite sorry about that. Let's print it 23, 11, 13, 10. That means we go depth first, right? 23, 11 and then 10 and then 13. 13, 10. I actually caught a mistake here. In depth first search, we are basically first of all inserting the left node and then the right node, right? So I think this order needs to be inverted. We will first insert the right node and then only the left node, and this will do the trick here. We say 23, 11, 10, 13. Yeah, 23, 11, 10, 13. In this case, breadth first as well as depth first search has happened to be similar, but this may not be the case always. So let us try to remove one of the keys. I say remove bst dot remove, I remove 10. So if I remove 10 and then run again to print breadth first list, I will only print breadth first for now. So yeah, 10 is removed, right? So if 10 is removed, then the node will the tree will look like this. So breadth first means first 23 and 11 and 13. 23, 11, 13. So yeah, this is working. So if you want to extend this, then you can do it in your leisure time, or if you guys need any help, then I'm always available on the social media. So yeah, binary search tree, we have already implemented it. So congratulations. Let's read some of the comments here. If you guys are just joining me in this session, and if you haven't subscribed it, then I would highly appreciate if you would subscribe to my channel. We have the target of reaching 400 subscribers today. I don't know how much we have reached. I will check it out later. So let's go on to another topic. So basically this new topic is complete binary tree. So we understood what binary tree is, what binary search tree is, and how to construct it, how to basically search through it, how to add a value to it, how to remove a value to it from it, and then we come to complete binary tree. So a tree is said to be complete if all of the labels except the last label is completely filled, and the leaves on the last label, these leaves are as far left as possible. They are stuck on the left side. For visualization, you can assume that there is a magnet on the left side, and all of the nodes are pulled by that magnet. So basically this tree right here, it is a complete binary tree because all of the nodes except the last node, actually in this case the last node is also filled completely, but that is not the requirement. All of the node except the last node, that means these labels, all of the labels except the last label is completely filled, right? Because a has two children, it has left child as well as right child, so it is completely filled. And the leaves on the last label are as far left as possible. That means right, in this case they are as far as left as possible. There is nothing you can do to shift these nodes even to the left side. So this is a complete binary tree. I will show you what a complete binary tree is not. Actually this is also a complete binary tree, if you can see, because I had given you an example of a magnet being here. If you assume that there is a magnet in the left side, and then all of the leaves, the leaf nodes are as far left as possible, just like there is a magnet here and the magnet is pulling them as left as possible. So all of the labels except the last label is completely filled. We do not have the last label completely filled, but we can have that exception because last label need not to be completely filled, but what we need is that the leaves on the last label should be as far left as possible. But if we see another example here, this is not a complete binary tree, because this is not a complete binary tree because this F node here right now, it is sitting as a left child of the C node, but there is a vacant space here. The B doesn't have right child. So if you assume there is a magnet here, this F should have been at the place of the right child of B, right? Because all of the leaf nodes should be as far left as possible. There is still a possibility of F going to this place, and this is vacant, so F is not as far left as possible. So this is not a complete binary tree. But now if we pull that F and we insert it as a right child of B, then this is complete binary tree because all of the leaf nodes are as far left as possible, and we have all of the labels except the last label is completely filled. So actually I'm discussing complete binary tree here because we will use complete binary tree for implementing heap data structure later on. So complete binary tree can be represented as an array, and a complete binary tree with n nodes can be represented by an array of n elements. So if we have a complete binary tree as such, A, B, C, D, F, then this can be represented by this array A, B, C, D, F. So basically the idea is going from top to bottom and left to right fashion, just like you write something on a paper. You start from top, you go on writing left to right, and then you come to the next line, left to right, next line, left to right, something like that. For array representation, A and then coming to next line, B, C, and coming to next line, D, F, A, B, C, D, F. This is the array representation. seeing this in more detail, we can see that this is the array representation, this is the tree representation. Actually, I'm assuming that the index of array is starting from 1 for simplicity. And basically, if you look at this A, B, C, D, E, F, G, and we inserted it into the tree representation, and if you clearly see, if you closely see here, the item A is on the index 1, right? So if the item A is on the index 1, then the left child of item A is on the index 2. That means just double of the index it is currently on, right? That means if B is on index 2, then its left child D is on index 2 times 2, that is 4. If C is on index 3, then to go to the index of its left child, we have to go to 3 times 2 equals to 6. And then basically, if you want to go to the right child, you have to go 2 times 2 plus 1. And for going to right child of C, you have to basically multiply it by 2 and then add 1. 3 times 2 plus 1, that is 7. So if we see, the left child of I index will be at 2i, and the right child of I index will be at 2i plus 1. And if you want to find the parent, you can clearly do that by doing C. From C, if you want to go back to A, then you have to divide by 2, and then you take floor of it, the floor division. Floor division basically means that you ignore the decimal part and then you consider only the integer part. That is floor I by 2. So that put aside, let us go to discuss heap. A heap is a complete binary tree where every node satisfies heap invariant property. Basically, it is a complete binary tree and it satisfies the heap invariant property. What in heap invariant property is, it is basically, it states that for every node in a heap, the node must be less than both of its child, and that is in case of min heap. Or if we have max heap, the node must be greater than both of its child. Actually, here is a difference between binary search tree and heap. In binary search tree, you need to have all of the nodes in the left subtree less than particular node, and all of the nodes in the right subtree greater than particular node. But in case of heap, you need to have all or particular node greater than both of its node or less than both of its node. And depending on that, we have two kinds of heap, min heap and max heap. So let us first see what max heap is. Max heap is a kind of heap where every node has values greater than both of its child. So 76 has child 12 and 55, and 76 is greater than 12, 76 is greater than 55. Both of its children, the value 76 is greater than both of its children. If you see 55, it is greater than 3, it is greater than 33. 12 is greater than 1, 12 is greater than 10. Yeah, this is a max heap. And if we consider min heap, then it is a special type of heap that has values less than both of its child. And in this case, 7 is less than 12, 7 is less than 8, it is less than both of its child. 12 is less than 14, 12 is less than 76, 8 is less than 33, 8 is less than 99. And for this session, we will only cover min heap because we have limited time, and if you know the concept of min heap, you can easily implement max heap as well. If we see some of the examples here, we can see what heaps are and what heaps are not. If you see this tree, it is not a heap. You can clearly see the reason, because this particular node 12 has 3 children, and if it has 3 children, then it is not a binary tree, and if it is not a binary tree, then it is not a heap. Now this is a binary tree, but this is not a heap because the binary tree is not complete. For it to be complete, all the labels except the last label need to be completely filled, but in this case the second last label is not completely filled. We have a vacant position here, right? So this is not a complete binary tree, and so this is not a heap. Now let us see here. This is a binary tree, but still this is not a heap because it is not a complete binary tree. For it to be complete binary tree, all of the leaf nodes should be as far left as possible. If we imagine a magnet here, then this 33 should come to this side, to the left side, right? So this is not a heap. But now, if we consider this tree in particular, still this is not a this is not a heap. Actually it is a complete binary tree, but this is not a heap. Do you want to know why? Because you can see the node 12 here. 12 is less than 15, but 12 is greater than 10. Actually, if we consider min heap here, all of the nodes should have values less than its children, right? So 65 is less than 78, 7 is less than 12 as well as 65, but 12 is not less than 10. So this is not a heap. But finally, if we put 10 here and then 15 and 12 here, we can see that this is a min heap, because the minimum element is on the root, and 7 is less than 10, 7 is less than 65, 65 is less than 78, 10 is less than 12, 10 is less than 15. So if we see the operations on min heap, we can see three main operations. We can either insert a value into the heap, and we can either extract minimum. That means we remove the root of the heap, because in the min heap the minimum element will always be on the root of the tree. And then pick means we return the item at the root, but we do not remove the item at the root. We only just see it, we do not remove it. So yeah, let us see the insertion operation into the min heap. Suppose we have a heap here. This is actually a heap, because you can see that 7 is less than 10, 7 is less than 65, 65 less than 78, 10 is less than 12 as well as 15. This is a min heap, and we want to insert 6 into this heap. So first of all, what we will do is we will insert the item as far left as possible on the bottommost level. So the place possible as far as left possible is here, right? So we insert 6 into this tree. But after inserting 6, we can clearly see that this violates heap invariant property, because the 6 is less than 65, but actually this is a min heap, so 65 should have been greater than 78, as well as this node 65 should have been greater than 65 should have been less than 78, as well as 65 should have been less than 6 also, but this is not the case here. So we are violating heap invariant property here, and we will just have to swap it with the parent. So if the item is smaller than its parent, then we swap it with the parent. So 6 goes up, 65 comes down. Now we check again, is the heap invariant property satisfied? Let us see. 7 is less than 10, but 7 is not less than 6. So heap invariant property is not satisfied again. It is not still satisfied, right? So we check the parent. If the parent is greater, then we just swap it with parent. 6 goes up, 7 comes down. Now we check, is the heap invariant now satisfied? 6 is less than 10, 6 is less than 7, 7 less than both of its child, 10 less than both of its child. Yeah, this is satisfying the heap invariant property. So we basically repeat that step until and unless the heap invariant property is satisfied, or we have gradually reached the root node. And this process of lifting up a node in the tree until we reach the root node, or until we satisfy the heap invariant property, is actually sometimes called as bubble up operation or swim operation. Basically swimming means you come to the surface of the water, right? So yeah, and we can clearly see that inserting at the last position was constant time O of 1, because you can instantly do it. But to reinforce the heap invariant property, you would have to gradually swap and come to the parent, and swap with the parent, and you would have to come to the root on the worst case. So the overall complexity will be O of log n. Now extract minimum, that means removing the minimum value from the heap itself. The item at the root is needed to be removed and returned, right? So to remove it, we cannot remove it directly, right? Because if we remove it directly, then there will be null in the root. So first of all, what we will do is we will try to search for the last element in the heap. That means the last rightmost leaf node, and we just basically replace the node with the node to be deleted. So 65 goes there, and 6 comes to the last node, right? Now we can safely delete 6. We can delete the rightmost leaf node. Okay, 6 is deleted, but now we have a problem here. The problem is that 65 should be less than 10, 65 should be less than 7. That means 65 violates heap invariant property here, because it is not less than 10, it is not less than 7. So basically what we will have to do is we will have to push this 65 down into the tree, because it is heavier. We have to put it downwards. We have to put the lighter elements upwards, and we have to put heavier elements downwards. So basically what we will do is we will swap 65 with one of its children, either left subchild or the right child. But we have to check its left child as well as right child, and we will choose the minimum among 10 and 7. 7 is minimum, so we will swap with 7. Swap it with the child having the smaller value. That is what we are trying to do here. So 7 goes up and 65 comes down, and then we see 65 violates the heap invariant property again, because 65 should be less than 45. And now again we have to swap it with one of its children. 45, either 45 or the right child, but we do not have right child here, so we have to swap it with 45. So 45 goes up and 65 comes down, and in this case the heap invariant property is satisfied. And we repeat this step until and unless heap invariant property is satisfied, or we have finally reached a leaf node, and in this case the heap invariant property is satisfied, so we will stop here. This process of sinking down a node, putting it down into the tree, to the bottom of the tree, is known as bubble down operation, or it is also known as heapify operation. So you may need to understand these terms just in case someone asks you in the interview, what do you mean by heapify? And the complexity is O of log n, because swapping the root with the last will just be a constant time, but after that enforcing the heap invariant property will require log of n times, so the overall complexity will be O of log n. So now we are coming to the construction of a min heap. How do we construct min heap? And the problem is, given an array of items, how will you construct a heap? And there are two ways. One is a naive approach that constructs a heap on n log n, and there is a fluid construction algorithm that constructs the heap on O of n time. That is quite optimal. So looking about the naive construction, we will basically start with an empty heap, and then for each item in the given list, we will just insert the item into the heap. We have basically already covered the algorithm to insert the item into the heap, so this is basically very simple, very trivial, very naive. And this algorithm I have tried to trace it down here. So first of all, we have been passed 12, 27, 11, 7, 5, 9, 15, and we need to construct min heap. So first of all, we insert 12, we insert 27, we insert 11 as the rightmost rightmost node, and then basically here we can see that this violates heap invariant property, because 11 needs to be here and 12 needs to go down. So 11 gets swapped and 12 comes down, and then we insert 7 again, 7 here, and we will basically now again try to swap it with its parent, because 27 needs to be less than 7, right? So it goes up. Again, heap invariant property is not satisfied, because 11 is less than 12, but 11 is not less than 7, so 7 needs to go up. 7 goes up, and now heap invariant property is satisfied, because 7 is less than 11, 7 is less than 12, 11 is less than 27. Now it comes the turn of 5. We insert 5 here, but this will again violate the heap invariant property. So 5 should be greater than 11 here, because 11 is less than 27, but 11 is not less than 5. So we need to swap 11 and 5. 5 goes upwards. Now in this subtree, all is good. 5 is less than 27, 5 is less than 11. But if we see the root node, 7 is less than 12, but 7 is not less than 5. So 5 needs to go up again. 5 less than 7, 5 less than 12, 7 less than 27, 7 less than 11. So yeah, heap invariant property is satisfied. We go to the next insertion. Insert 9 here, and again we can see that 12 is not less than 9, so we go upwards. And in this case 5 is less than 9, so yeah, we do not need to go upwards again. We can stop here, and we insert 15. And in this case the heap invariant property is instantly satisfied, because 9 is less than 12, 9 is less than 15. So yeah, we have already constructed the entire tree. And basically what we are doing is we are inserting n items, and each of the insertion is log n time, so the overall complexity is O of n log n. And then we come to the next optimal construction algorithm. This is fluids construction, and this algorithm basically constructs the heap on O of n time on average. And the idea is basically to construct the heap in place. In place means you modify a given array itself to make the heap. And the idea is that the leaf nodes are already satisfying the heap invariant property, so we need not do any operations on them. So we start from second last node and we traverse backwards, and for each item we perform heapify operations, which is also known as sink or bubble down operation. We will see this graphically in an example. So we have the same construction here, the same list is given, and then we will begin with the the given array itself. We will insert 12, 27, 11, 7, 5, 9, 11 in place. We are trying to do in place construction, right? So we will first assume that the given item is already a heap, and then we will start to update the values so that it satisfies heap invariant property. So yeah, we have this 12, 27, 11, 7, 5, 9, 15 here. And now the assumption is that the leaf nodes already satisfy heap invariant property. So for any binary search tree, a complete binary search tree, you can prove that half of the node will lie on the leaf node. Okay, that is generally the case. About half of the node will already be on the leaf node. So if we consider that the leaf nodes are already satisfying heap invariant property, then we are basically already cutting off half of the nodes, and we are only applying operation to the next half, right? So we will not apply operation to these nodes. We will not apply operations to 7, 5, 9 and 15. So we will begin from the second last level, that is the level 11. So we will start from 11, start from the second last level, and we will traverse backwards. So that means we will start from 11 and then traverse backwards. And then basically 11 does not satisfy heap invariant property, because 11 should be less than 9 and it should be less than 15. It actually is less than 15, but it is not less than 9. So basically we have to swap it. 9 goes upwards, 11 comes downwards. We are basically performing bubble down operation here, and yes, the heap invariant property is satisfied. And now we move this arrow backwards to 27, and then we try to heapify 27. That means we try to bubble down 27. 27 is it is not less than 7, it is not less than 5. So we will choose one of the smaller elements of 27, and one of the smaller elements among its left and right child. That means 5 is the smaller element between 7 and 5, so we swap 27 with 5. Yeah, now it is this particular subtree is satisfying the heap invariant property. We are not concerning with the overall heap invariant property of the overall tree, because we are just we still have to go to this root node, right? We still have to traverse there, but in this subtree the heap invariant property is already satisfied. So now move this arrow backwards. We are traversing backwards, and then we go to 12, and we see 12 is not less than 5, 12 is not less than 9. So we will try to replace this node with the smaller of these two, and 5 will be the smaller between 5 and 9. So we basically have to swap. 5 goes upwards and 12 comes downwards. Okay, now again we see 12 is not less than 7, 12 is less than 27, but 12 is not less than 7. So basically what we will do is we will replace 7, and we will swap 7 and 12. So 7 goes up, 12 comes down, and then finally we see that we have successfully constructed the heap. This algorithm is quite surprisingly O of n. I will not give the mathematical treatment as well as mathematical derivation here, but you can see the mathematical derivation on the link in the description. I will leave that for you guys to discover. This algorithm is O of n. It is already mathematically proved. Basically you will have some kind of Taylor series there, and you will have infinite power series sum, and which will basically reduce to infinite geometrical series sum, and then it will be surprisingly O of n. You can see the mathematical derivation on the link in the description. So on average, as a summary, we can see that insertion is log n, extract minimum is log n, picking is O of 1 because we instantly can look upon the root and return the value, bubble down is log n, and construct is O of n. And the applications of heap, if we see, we can see that heap is extensively used in heap sort algorithm and implementation of priority queues as well. And heap implemented priority queues are used in algorithms like the extras algorithm, prims algorithm, and so on. So it is very useful. We will now go on to implement heap in our code. In case you guys have any problem or confusion understanding, you can guys ask on the comments on the chat box. And if you guys are new and you haven't subscribed yet, I will request you to subscribe to my channel. So I will go to data structures here, and then go on to heap.py. So yeah, first of all, I will have to declare class for heap, right? So basically we have already discussed how to represent a complete binary tree with an array. So we will implement our heap with an array. So first of all, I will create a class called minHeap, and I will define an empty constructor, take self and items, which will be by default empty list. I will say self.nodes equals to an empty array because we are implementing the heap as an array, right? And self dot we are trying to construct the heap, right? So we will write something like to do construct the heap with items. We will write that method or code sometime later. We will just come down here. So yeah, we will not do constructing the heap in naive fashion or the trivial fashion, but we will consider constructing the heap in log n time, in O of n time, and that means the optimal time. So first of all, we will go on to implement some of the other methods, for example swim operation. Basically swim is also called as bubble down, bubble up. Swim means to go upwards, right? So bubble up or swim, these are synonymous. You can use any one of them. And I will also write a method called sink. This means to go down. Okay, I will write them later. I'm just writing the prototype here first. And also I will write def extract min. What it will do is just it returns self.delete 0, right? And I will write delete also, self.def delete. That means deleting the node with index I. I will write it later. And basically, yeah, let's try writing our code. So first of all, I will create some of the helper methods, basically to access a child node as well as access a parent node. So if I say def parent of I, then it has to return me I floor division 2, right? And if I say right child and pass I, it will have to give me 2 times I plus 1, right? If I say left child it has to return me 2i. Basically, we already discussed this when we were discussing how to implement a complete binary tree using an array. So let us first of all do swim operation. Would that be okay? I think so. Yeah. So suppose I have a node at index I, and then I want to swim. I want to take this. I want to bubble up and then take this node upwards if this breaks the heap invariant property. So first of all, what I'll do is I will say p equals to self.parent of I. I have to first of all find the parent of I, right? So while I is not equals to 0 and self.nodes p, that means parent, is greater than self.nodes I, that means the parent is greater than the parent is greater than the current node, then we need to swap, right? Because this node needs to go to the parent and the parent needs to come down. So let us write another method for swapping also. Let's say def swap self I j, and basically the swapping is done by self.nodes I comma self.nodes j is equals to self.nodes j comma self.nodes I. This is basically swapping the value at indices I and j. So in this case we do self.swap I and p, and we say I equals to p, because for next iteration we have already gone to the parent, and parent will be the current node, and we will say p equals to self.parent I. This is just recursively going upwards, right, until and unless we reach to the root node, or the heap invariant property is no longer violated. So this is swim operation, we go upwards. Now let's come to sync operation. So let us write def sync, and we start from I, right? So basically we say L equals to self dot left child of I, and R equals to self dot right child of I. We basically find left as well as right child first of all, and then we will check that while L is less than length of self.nodes, that means we haven't gone out of the bounds of the array itself, because if we are trying to find the left child of the last index, it will give me some value that is greater than the length of the total number of nodes. So this should be checked, and as well as R is less than length of self.nodes, and if we see some violation in the heap invariant property, and that violation will be something like self.nodes I, it is greater than self.nodes in left child if the current node is greater than left child, or self.nodes I is less than self.nodes R, that means if the current node is greater than left child or the current node is greater than right child. In both of the case the heap invariant property is it is violated, and in that case what I want to do is I want to basically, Let's read the comments here. I think someone is here. Oops, nope. Okay. So yeah, if the heap invariant property is violated, then we have to choose the minimum between the left as well as right, right? So if R is okay, in that case I want to, you know, say min value equals to minimum of self dot nodes left and self dot nodes right. But you know, this may produce, okay, this will not produce exception because we have already checked that R is within the limits of you know, self dot nodes. Yeah. But actually I want this to be quite versatile, you know, if L is within the lane, within the bounds, but R is not within the bounds, and in that case also I want to let user to, you know, to do the sync operation. So I will put OR here, and then I will basically check if, you know, any one of them is you know, out of the bound or not. So what I'll do is, first of all I will check, you know, if L is, you know, greater than or equals to length of self dot nodes, then in that case basically I will say min underscore value equals to self dot, I think min value index would be better here, min value index equals to R, because L is already out of bounds. So we will have minimum value in the right subtree or the right child, and you know, if R is greater than or equals to length of self dot you know, I don't know, self dot nodes, then in that case a min value index equals to L, and else if that is not the case, then min value index will be minimum of we have to check the minimum value, right? So yeah, we will have to again check if self dot nodes L is less than self dot nodes R. In that case we will say min value index will equals to L, else we will say min underscore value index will equals to R. And basically we will need to swap the values here. I will say self dot swap, and then I swap I with min value index. Now I will get swapped with min value index, and then I will, you know, say I equals to min value index. Okay, I think that will work. If not, we will go on and edit it later. Basically what I'm trying to do is I'm you know, finding the left child of I am finding the right child of I, and then while L is less than, you know, this is basically checking whether the L and R are within the bounds, and if heap invariant property is satisfied or not. Basically, if I is less than self.nodes L, then this is this is it violates the heap invariant property. So this is basically saying that unless we have until we have heap invariant property is violated, and the L and R are within our bounds, so we will go on to swap the current index node with the minimum value among its left or right child. So basically this is what this code is doing. And now let's come down here. This sink is also called heapify. Okay, so now if we come down, then we will have to write removal algorithm as well as insertion algorithm. I haven't written insertion, I haven't written removal, that means the extract min algorithm. And yep, so basically let us write the algorithm for inserting into the min heap. So def add self data. Basically what we will do is we will first add the item at the end of the heap, that means at the end of the array, right? So yeah, we will add the item at the end of the array. So that means we will do self.nodes.append, and we insert data into it. This data is item actually, and we append into our this array. And after insertion there may be some violation of heap invariant property. In that case we will have to do self.swim, we have to do bubble up operation, and starting from where? Starting from length of self.nodes -1. That means starting from the node we just inserted, we have to gradually swim operation, so that heap invariant property is again enforced by force. So yeah, this will be addition. And now we need to delete a particular node. So yeah, let's come down here, def delete. So first delete, for deleting we actually have to follow some steps. First of all, we have to swap the root or swap the item to be deleted with the last item in the list, right? But I think we do not need this delete method. Actually, I'll just comment it. I don't know what made me think that I will need it, but anyway, I will first write extract min itself. I will not just call self.delete, but I will just write algorithm for the deletion itself. So if I come to sync here, I'm actually syncing from I index. So what I'll do is for extracting minimum, what I'll do is I'll first try to find last position in our array. The last position will always be the length of the array -1, because our index starts from 0, right? So I will then swap the root with the last element, right? So self dot nodes I not I, we will do 0, that means the root, and self.nodes last will be equals to self.nodes last self.nodes 0. Okay, so far so good. We just swapped the root with the last element. Now we need to delete the last element, right? So to delete it, we will just say, you know, data equals to self.nodes.pop. Pop deletes the last element from the array, and we are basically storing the data because we need to return it, right? Extract mean will remove as well as return the root element, so we store it in data. And after actually, you know, deleting it and after actually swapping the root with the last element, now we need to sync, we need to heapify, right now, because our swap may have broken the heap invariant property, and we need to reinforce the heap invariant property by ourselves. So what I'll do is self.sync, and I will do I, self.sync I. Sorry, I already have written this sync method. I will just delete it. And yeah, so this is it. And in case our heap is empty at first, then basically this self.nodes length of self nodes will give 0, and 0 minus 1 will give -1, and then this algorithm will not work as expected. So what I'll do is I will put it inside the try catch block, and in case some exception occur, what I'll say is I will say the heap is empty. So yeah, I think I have completed, I have done all of the methods here, and just the remaining code to write is, you know, to construct the heap with items, right? So we haven't written that particular algorithm. So first I will just call construct heap and pass, you know, items, and I will write construct heap here. Okay, basically we had already, you know, discussed about the assumption that this optimal algorithm makes. I am actually writing this optimal algorithm. Okay, optimal O of n times. In our assumption, we had actually assumed that the leaf nodes are already satisfying the heap invariant property, so that we will only start to heapify from, you know, the second last element, the second last index. So what I'll do is, you know, I will say self.nodes equals to items, because we are trying to construct in place. That means we will basically say that our nodes is equal to the items itself, and then we will only try to, you know, reinforce the heap invariant property. So we will say n equals to length of data, and then we will start for I in range n minus 1 divided by 2. That means we will start from the second last label, right? If we do n minus 1 and divide it by 2, this will give me the last item in the second last label. You can check it out mathematically too. And you know, I will reach up to 0, and for reaching up to 0 I will have to put -1, because this second argument is not inclusive, it is exclusive. That means if I put -1 here, the loop will reach only up to 0. If I put 0 here, the loop will only reach up to 1, and we will provide the step as -1. That means this is basically saying that our value for I will be ranging from this particular value up to 0. For 0 we have to write -1, because this is not inclusive, up to 0, and our step size is -1. That means basically we are going in the decreasing fashion. So for that range, what I'll do is I'll do self.sync I. So just hoping and finger crossing this will work. I don't know if it does or not. Let's try. Let's go to examples and create heap.py. So from data structures.heap import min heap, I think, yeah, heap equals to min heap, and I try to construct min heap from 1 4 3 5 2 or something like that. Okay, and then I want to print the heap. Basically what I'll try to do is for I in range 5, there are 5 elements. I will just try to print heap dot extract min. Basically this should first of all give me 1, then give me 2, then give me 3, then give me 4, then give me 5, right? Because basically extract min will give me the minimum element in that heap. So this will basically help me to test my code whether it is working or not. So yeah, I will try to run it. Okay, this was expected. Name data is not defined. So let's go to line 8 in heap.py. Line number 8, len data. Actually this is not data, this is items, right? Okay, go here, run it. List index is out of range, and I think I have to test the bounds for I also. Should I? I think I should. Where is yeah, here. L is less than len self dot nodes, or R is less than len self dot right nodes, and I is less than len self dot nodes. So basically go to this example and run it. This is lists index out of range. So let us see. Actually guys, if you can see some error in my code, then you can tell me also, because it's kind of a continuous process. It's a give and take. You might have noticed something that I might not have, so feel free to suggest me anything or any error you see here. So basically the error comes from line number 10 first, construct heap, and then it goes to line number 40 and here, right? So what I'll do is actually I will try to print I here, just so that I will see what value I is actually getting. The value of I is, and then try to run it from here. The value of I is 2, and the list index is out of range. So I is not the issue here. Okay, I is not the issue. Let's try printing the value of L is L, and print the value of R is R. So if we go here and run it, so we can see that the value of L is 4, the value of R is 5, and 0, 1, 2, 3, 4. So the 5 index does not exist on the array, so this is giving me the list index out of range. So I don't know why R is getting 5 here. So I is 2, and then basically let us visualize this. Okay, I'll try to visualize it first. First of all, I am doing in place. So 1 is here, 4 comes here, 3 comes here, 5 comes here, and 2 comes here. Okay, and then for I equals to 2, that means 0. Okay, guys, I think I have found a mistake here. I think I found the culprit, because actually my assumption was that array is index 1 based, right? Because array index starts from 1. I was assuming that from the start, but in our practice, actually our array index is starting from 0. So basically yeah, this one, the parent, left child and right child, these indices will not quite actually work properly when the array index is 0 based, right? So for that I will actually have to do I minus 1 divide by 2, and in the right child I will have to do I 2 times I plus 2, and on the left side I will have to do 2 times I plus 1. This is basically because I will have to address for indices starting from 0 and indices not starting from 1. So yeah, that was quite a nifty error, but I don't know if this runs again. Okay, line number 65. Line number 65, and I is not defined. Okay, it is not self.sync 0, but it is not self.sync I, but it is self.sync 0, because I'm basically trying to sync from the root node. Okay, I'll try to run it again. Is this loop running? I think I have encountered an infinite loop here. This loop is not ending. So actually the sync operation is my main culprit here. So yeah, for syncing I actually start by storing the left child on the L and right child on the R. The value of I is 2, that means 0, 1, 2. Yeah, I is 2 from here, and I is 4 here, but it is saying 5. This is giving me so hard time. Programming is 5% writing the code and 95% debugging the error you have written. Certainly in this sort of scenarios, I remember that quote. What if I put and here? Will this cause an error? I don't know. What time is it now? It's already 2:37. Quite a lot of time. I think we'll have to postpone the Fenwick trees for other session today too. Let me write this code from beginning again. Hopefully I'll find something. If I try to do by explaining, then I will have more probability that I will get it right. So yeah, first of all, I'm trying to sync from basically I think the sync operation, I do not need to provide I also, because it is always provided at 0. So I will just drop that and equal to 0.
I'm not sure I understand.
I equals to 0 and L equals to self dot left child, I R equals to self dot right child, I. Among these two, if one of if one of the L or R is out of the bounds, for example in this case the right will be out of bound. In that case I will have to replace it with the minimum of these two. What if I write sync as a recursive? I got another idea. Self I don't know. I'll try while self dot nodes I is greater than self dot nodes L, or self dot nodes I is less greater than self dot nodes are. This means the heap invariant properties but in this case, you know, for doing this we will have to check if you know L is less than length of self dot nodes, as well as R is less than self dot nodes itself. I think the error was due to, you know, me doing actually I was doing AND here. Okay. Is lane of self nodes. Okay, inside it let's do something like if self dot nodes L, that is the left child, is less than self dot nodes R, or self dot nodes L is equals to self dot R. In that case we will swap with left child and self dot nodes L comma self dot nodes I will equals to self dot nodes I comma self dot nodes L, right? And I will just do I equals to 1, I equals to sorry L, because we are you know, gradually going towards the left, and else if this is not the case then self dot nodes right comma self dot nodes I basically will be self dot nodes I comma self dot nodes R. We are swapping value. Basically this is the syntax of swapping the values in Python, right? So I will just do I equals to R, and then inside this while I will say L equals to self dot right child. I don't know what it was. Self dot right child. Okay. Self dot right child of I, and R equals to self dot, sorry it is left child, and R equals to self dot right child of I. Okay, I'm trying to rewrite the basic the same function, and extract mean, indentation is wrong. Oh, okay, I basically try, but I need not to try there, sorry. Sync takes one positional argument but two were given. In construct heap, I need not pass self.sync. Yeah, okay. I basically I assumed that the sync will always start from root node, but actually that is not the case. My mind is not working properly, so pardon me for that. And save it, coming down, calling with 0, save it, and go to heap.py. Okay, basically I'm getting none for each of them. This is quite unexpected. At least the exception is not coming. I'm happy for that. Oh, I forgot to return. Yeah, I forgot to return the data. Sorry for that. Coming back to heap.py. Oh my god, it is about to work now. 1 2 3 5 4. One, two, three, five, 4. I think it has something to do with let us try to trace it first. First of all, we want to remove the root, right? So we want to remove 1, and then we try to replace 1 with 2, and 1 comes here. We remove 1, and then starting from root we sync down, but in this case there is no need to sync down, so it is okay. And for the next time we want to replace this with 5, and 2 comes here, and we basically remove 2, and now 5 needs to be synced down. 3 comes here, 5 goes here, right? In the next time 3 comes out, 5 goes here, 3 comes here, and 3 is deleted. And in the next time yeah, this is the case where it is not working. Only one child is there, but I am enforcing both of the condition to be to be out, over and out. So yeah, this is working for kind of a complete heap, for completely filled binary tree, but not for partially filled, that is for the 5 elements. But for example, if I put 6 and 7 here, I think this should be working, if I'm not wrong. Not up to 5, but if I put up to 7, yeah, this is working for 1 2 3 4 5 6 7, because if you want to know what actually is happening, is because I have basically enforced both of the left as well as right to be less than length of the self dot nodes, right? But in particular case, when the case reaches this particular scenario, here the 5 has only left node and the 5 doesn't have a right node, right? So in this case, basically this while loop is automatically this ends, this loop ends. So yeah, we did not get the result as expected. Now we need to modify our code just to ensure that we if we put or here, then that will certainly not work. I think I will leave it for now. This code is working for completely filled binary tree, and I think I will try to cover how to change this particular code to cover for the case where there is incomplete binary tree, because we have already gone past the scheduled time for this session. I actually had planned this to become 2 hours, but we are way more into it than that. So actually I'm going to end this session here, and I will answer some of your queries right now. If you guys are still with me, then please ask any queries if you have related to Python, or anything related to computers or programming in general, and I will answer those questions for some amount of time, and then I will end this session.